In the first part, I told you about two-component fermions and how many of their properties are really determined by the S-wave scattering lengths. And so what I like to do in the second part is switch to a single-component boson system, so just one species, and show you that in this case, in addition to the S-wave scattering lengths, we also need a three-body parameter. So that's sort of the major change. And this goes in hand with like fermions avoid each other, so we have the Pauli exclusion principle that helps us out. But if we have bosons, we don't have this Pauli exclusion principle. And so in some sense, we need something else to prevent the bosons to just crashing into each other. And it turns out that in some sense, the three-body parameter does take care of this. So to discuss this, I want to again start with three particles and sort of look at the case where the S-wave scattering length is infinitely large. And in this case, it turns out that the hyperradial and the hyperangular motion separate exactly, and the hyperradius squared is just proportional to the distance between particles 1 and 2 squared, the distance between particles 1 and 3 squared, and the distance of particles 2 and 3 squared. So we have this separation here, and I'm not going to go through the solution of the hyperangular equation, but it turns out that that gives us an eigenvalue, which I've called I times S naught here, where S naught is 1.006. And I'm assuming identical bosons here. And this eigenvalue enters in the Schrödinger-like equation for the hyperradius, and that's entering in this way. So we have the kinetic energy of the hyperradius, and then we have this effective potential in the hyperradial degree of freedom. And you can see that if we square I times S naught squared, we actually get a negative sign. And this means that if we solve the equation, we actually get an infinite number of bound states in this 1 over R squared potential. I'm not going to show this explicitly how to derive this, but it's a very unique type of system. We have a 1 over R squared dependence, and so this gives rise to an infinite number of solutions. So if we take a solution and say this has an energy of E3n, then we can scale the solution by a factor of 22.7, which is given by this S naught value here. And we find a new solution that has an energy that's lambda squared smaller than the energy we started off with. So in this infinite ladder of states, the energy levels are spaced by a factor of 22.7 squared. That's about 515. So this is sort of the picture that emerges, which within a zero-range framework for three identical bosons with infinitely large S-wave scattering lengths. We have this infinite ladder of states where the energies are spaced by a factor of 515, and the size of the system increases by a factor of 22.7 as we go up in energy. Just to sort of show you the scaling, I've schematically indicated our trimer here, depicted as Borromean rings. This is about a factor of 22.7 bigger, and the next one looks identical, and again is a factor of 22.7 bigger. And these Borromean rings also show us something else. If we do have an infinitely large scattering length, the dimer is just at the verge of being bound or not bound. So if we look at these rings, we see that the blue ring is really sitting underneath the green ring. So if we take away that red ring, cut it open, then the blue-green dimer is actually unbound. So we really need all three particles to have these three-body bound states in the Borromean regime, in the regime where the dimer is not bound. So this picture here that I've shown you is for the infinite scattering length case. And we have this infinite ladder of states. Say this is my infinite ladder of states. The rungs are not separated by 22.7 each. I can't do that. But what I haven't told you is how this ladder is actually located, or where this ladder is located on the absolute energy scale. So all these states here are orthogonal to each other. But if I shift the ladder a tiny bit, I get a new set of states. They're also orthogonal to each other, but they're not orthogonal to the first set of states that I had. So in some sense, I need something that's sort of fixing where my ladder sits on the energy scale, and that something is the three-body parameter. And if I fix the three-body parameter, it's just one more input parameter into the theory, then I get this energy spectrum as a function of the S-wave scattering lengths. So what this parameter does, it fixes where the energy levels sit at unitarity, which is the point that I've shown here in the middle, but it also automatically fixes how the spectrum looks like for all other S-wave scattering lengths. So this energy spectrum that I'm showing you is fully determined by the S-wave scattering lengths and one other input parameter, the three-body parameter. And again, this is done in terms of the zero-range framework. And if you look at this spectrum long enough, you'll see that there are actually a couple of very unique features about this. So to think about this, I prefer to take sort of a square well potential and say, as I go to the right, the attraction is actually becoming stronger, the potential is getting deeper. And what you see here is, as I go to the right, one after the other, I'm actually losing these trimers. These trimers are running into the atom dimer threshold, and one after the other is disappearing, even though the potential is getting deeper, if we think in terms of a square well potential. And on the other side here, this regime here, we have the trimers running into the three-atom continuum. So we have the three-atom threshold sitting up here. So this is the Efimov plot, which really has rather unique features. There's also this factor of 515 or 22.7 squared that really shows up in different places on this plot. And Rudy will tell you a little bit more about how these regions where we run into the three-atom threshold or into the atom dimer threshold, how these special points can be probed experimentally. What I like to do is I sort of like to take this and say, what happens now if we place this three-body system, the three-body Efimov states, into a harmonic potential? So the first thing to realize is, and this is not specific to the trapping potential, that there actually does exist the smallest trimer. So it's not like we can make these trimers really, really small, or there's make them smaller and smaller. No, because we do have in the realistic atomic systems, we do have a van der Waals length. This van der Waals length sets a cutoff, and the smallest Efimov trimer certainly can't be smaller than the van der Waals scale. So we sort of have a bottom of our rung. And then if we turn on the trap, you might say, okay, we have the smallest trimer, we have another trimer, but eventually the trap is actually going to cut off the bigger trimers, the bigger Efimov trimers, simply because the trimers don't fit into the trap anymore. So if we then put this together, what we expect is that if we look at the spectrum of the trapped three-body system, that we have three-body states in the trap that are essentially just squished versions of the free space trimers, and that these states do depend on the three-body parameter. And then we also expect to have states that live in the trap that are actually largely independent of the three-body parameter. And that has to do with the fact that we also have these hyperangular eigenvalues that are actually not imaginary, but that have real eigenvalues and that do not give rise to an infinite number of bound states. And so if we look at this in a little bit more detail, that's exactly what was found. The first study on this that I know about was by Pathak and co-workers. And what I'm showing here is for fixed S-wave scattering lengths. So this is now not at unitarity, but a scattering length of 1. As a function of the three-body parameter, you see states that are essentially flat, these red guys, and then states that do depend on the three-body parameter. And these states have been termed non-universal states or Efimovian states. In reality, these states are actually not quite straight. This is sort of more of a cartoon, but there's actually a coupling between the hyperradial and hyperangular degrees of freedom if we had finite scattering lengths, and that leads to these avoided crossings here. But roughly, we can say we have a region where state has mostly Efimovian character, and we have a region where states have mostly universal or BEC character or three-atom character, whatever sort of language you prefer. On the right here, what I'm showing is the energy of three particles now as a function of the scattering lengths. So for change, the non-interacting system is actually in the middle of this plot. And what you see here is, as indicated by these bars, that there's a prediction that even in this regime, when the system is effectively non-interacting, the S-wave scattering length is 0, there's still predicted to be some dependence on a three-body parameter. So there's a later study that looks at the sort of similar systems, similar physics. This is by Werner and co-workers. And again, in the top plot here, what we have is the energy of three particles, three identical bosons and a trap. But these energies are now plotted as a function of the range of the two-body potential. This is using a separable two-body potential. And what you see is, you see this one state here that's depending on the range quite strongly, and this other state here that's relatively flat with respect to a change in the range. So this relatively flat state, that is this universal state, or that BEC state, three-atom state, and this guy that's moving down here and changing quite a bit with the range, that would be the Efimovian state. And just for comparison, the zero-range theory would actually predict these solid lines, so there's a little bit of a finite range effect as well. What I should say is that this is an example for an infinitely large S-wave scattering length. And within this finite range model, there's a very weak avoided crossing between the Efimovian state and the universal state. And one key point that this study really made is that the lifetime of the universal state, of the three-atom state, of the BEC state, so three-atom BEC state, is actually quite long. So the losses expressed in terms of the angular trapping frequency are tiny. So the phrasing tiny loss rate is taken directly from the abstract of that paper. And even the loss rate of the Efimovian state is actually not so bad, suggesting that these Efimov states in a trap could be populated. And in fact, there is a recent study from Eric Cornell's group that reports on populating Efimov trimers in a trapped system by doing sweeps. So this is sort of the strongly interacting regime, and clearly there's a dependence on the three-body parameter. As the range of the interaction potential is changed, the three-body parameter actually changes, and that's why this Efimovian state is really changing with the range of the two-body potential. So what I like to do now is I sort of like to go back to this point here and the regime around the non-interacting limit. And I like to understand to which extent do we actually need, or to which extent is there a three-body parameter that plays in when the S-wave scattering length is really small. So in some sense, what I like to do is sort of connect this weakly interacting regime, which I think we typically think of as understanding very well, with the strongly interacting Efimov regime, where the S-wave scattering length is large. And to look at this weakly interacting regime, I'm going to use perturbation theory. The S-wave scattering length is a small parameter. So we're going to use the non-interacting Hamiltonian as as sort of the unperturbed Hamiltonian. We start with the unperturbed state, non-interacting state. And then we treat the interactions as a perturbation. And the idea is to sort of go from this picture here, where we have these bosons then interact, and due to the interactions, there can actually contributions to the of the excited state orbitals, going from this type of picture to going to an effective single mode picture, where we only have the lowest mode in our system, but instead have effective two-body interactions, effective three-body interactions, and effective four-body interactions. So sort of the language I'm using here in going from multi-band physics to single-band physics may seem a little bit much for just talking about a simple harmonic oscillator, but it's sort of motivated by the fact that the same type of thing can be done, say, for the Bose-Hubbard model, where you also have low or single-band Hamiltonian versus multi-band Hamiltonians. And so what we're interested in is how do these effective three-body two-body, three-body, four-body interactions look like, and what can we actually learn from them, and where do they show up in an actual experiment. So let me just sketch a little bit how we think about these. So we start off with the non-interacting ground state. So it's written as a Fock state here. We have our interactions here and our coupling strengths. And in first order perturbation theory, we just get an energy shift. And then in second order perturbation theory, I've written down the expression here. Things get a little bit more interesting because we have these excited states here that contribute where, say, two particles are promoted out of the lowest state into excited states and so on. And if we go through this, what we find is that we actually have to renormalize our coupling strengths by introducing a counter term. But also what you find is that at this level, at second order perturbation theory, we find effective two-body interactions and effective three-body interactions. So sort of physically, you can think about it this way. You have two particles come in, they collide. One particle gets promoted to an excited state, and that then collides with another ground state atom. And so we really have three particles involved in this collision. And because we have three particles, we actually have an effective three-body interaction. And it turns out that this effective three-body interaction is attractive, and this means that it could actually lead to a destabilization if we look at phases, say, within the Bose-Hubbard model, for example. So if we carry this through and go to higher order, then we find this breakdown into effective two-body, three-body, four-body, five-body interactions, where in first order perturbation theory, we get something proportional to AS. In second order, we get AS squared, third order, fourth order, and so on. And each time we get higher order, effective higher body interactions. Okay. So this is sort of the picture that emerges. And one of the questions is, why is this important? Well, as I mentioned already, the fact that the effective three-body interaction is negative could lead to a destabilization of phases if we look, for example, at similar physics within the Bose-Hubbard model. But there's also another reason why this is important. So say we take a rubidium-87 system in a trap, 3 kilohertz roughly. What one finds is that the effective two-body interaction is about a factor of 10 larger than the effective three-body interaction in magnitude. So you might say a factor of 10, that should be enough. So the effective three-body interactions should not matter. However, if you look at the fringe visibility, then you see that there's a significant impact. So what I mean by this is, let's say we take a very deep lattice, where each lattice side is basically sort of like a harmonic oscillator. And you load your system into it, so you have a state with 2, 3, 4 atoms per side. And you let the system evolve in there, so the interactions are on. And then you release the trap, and you look at the sort of interference pattern between the signals coming from the different individual optical lattice sites. And what you see is you actually see these effective multi-body interactions occurring as different energy scales or different time scales in the time signal. So, for example, in this experiment by Emanuel Bloch's group, they've actually measured the effective two-body interactions, effective three-body interactions, and effective four-body interactions. I should say this is for a system that has a fermion in it, but the physics is really very similar to just a pure bosonic system. So this way of thinking about the system in terms of not the true two-body interaction, but in terms of effective two-body, effective three-body, and effective four-body interactions, that's actually something that's measurable, and that's a nice way of thinking about the system. Different way of saying it is just, if you have two particles and you put a third one next to it, that one is actually pulling and pushing, and so the physics actually changes by having more particles in the system. So we have these effective interactions, and if we go back and you remember my motivation for looking at this, then I said, well, what I like to do with this is I actually like to look at the weakly interacting regime, and I like to see if there is a dependence on a real three-body parameter, even in the weakly interacting regime. And I actually haven't answered that question yet. And what I have to say is that when I showed you this slide here, I didn't tell you the full truth. What I mean by this is all these effective n-body interactions that I have here, they're all determined by the S-wave scattering lengths. What you find, however, is that the theory is not well defined at fourth order if you only keep the S-wave scattering lengths. And so what you find is that you actually do need to introduce sort of by hand a three-body potential. So this is an intrinsic three-body interaction that comes in at fourth order perturbation theory. You can see fairly easily that this should come in at fourth order perturbation theory, because if you analyze the units here, you see that the delta function has units of 1 over length cubed. This one has units of length over 1 over length cubed. And so this means that this coupling constant G3b that I define must have units of length to the 4, and that's exactly fourth order perturbation theory. So we do actually see that there is a three-body force that's needed, even in the weakly interacting regime, when the S-wave scattering length is not very large. But measuring this three-body force and this sort of three-body parameter in that regime is actually quite hard, because it typically has a small value. So maybe the last thing that I just touch on is we have this weakly interacting system now. We've described it in a trap. How does this connect to, again, sort of more of a many-body type viewpoint, and in this case, the Lee-Huang expansion. So in this expansion, which is for the homogeneous system, in the thermodynamic limit, we have that the energy per particle is given by this prefactor, sort of the mean field term, then we have quantum fluctuations on top of that, a logarithmic term, and then a term that depends on the three-body, or on a three-body parameter. And if you take the sort of things that I've shown you, and you take the leading order effect of two-body interaction, and you sort of do what I would refer to as an inverse local density approximation. So you take your trap and you say, let me just get the density for this trapped system. So I take the average trap density and relate it in this way to the number of particles. If you do this, you use the effect of two-body interaction, you find that you actually reproduce the leading order LHY term. So things are consistent. You're treating the system perturbatively, either in the trap or in free space, and you basically get the same mean field shift. So this is sort of ensuring. And of course, this LHY expansion here, that's been shown to work reasonably well up to sort of intermediate densities. To me, one thing that is always interesting is that this logarithmic term here, which is shown by this dashed or dotted line, that improves the description for a Bose gas only over a fairly small regime of densities, and then it really sort of goes nuts if you want. So the taking only the quantum fluctuations here does actually in many cases do a better job and leads to a better agreement with the hardcore Monte Carlo data. So maybe in terms of time, sort of running a little bit short, but mention just one more aspect, namely think about the Gross-Pitaevskii equation, which I'm sure many of you have seen in the context of treating bosons, and sort of the way to think about the Gross-Pitaevskii, or one way of thinking about it is that we have a test particle that is moving around in the mean field or the background atoms, so in a field that's created by the other n-1 atoms. And if we want to derive the Gross-Pitaevskii equation, we can again start with a many-body Hamiltonian, so a microscopic Hamiltonian, where we have kinetic energy for each particle, trapping potential for each particle. And we do have the interparticle interactions, which, you know, we could use a square well potential, hard sphere potential, a realistic van der Waals potential, or whatever we like. If we use a zero-range interaction or a pseudo-potential, just this zero-range interaction here, no regularization, and we use a simple product over single particle states. And we then take these two assumptions, zero-range interaction and the product state, we put that into our energy expectation value, our many-body energy expectation value, and we vary these single particle states phi, with respect to phi and phi star. What we find is we actually do get the Gross-Pitaevskii equation. And this really emphasizes that we can think about the Gross-Pitaevskii equation as the equation for a single atom that fields the mean field, the average of the other n-1 particles. And of course, we can then say all the atoms behave in the same way. So this is actually a BEC wave function. And so I think this is sort of another nice connection between a more microscopic way of thinking and a more macroscopic way of thinking about the problem. So this is sort of coming back to the outline of this lecture. So I told you a little bit about two-body interactions and the S-wave scattering lengths. I talked about 2, 3, and more particles in a trap. I focused on fermions and on bosons. And sort of the last point that I want to make is that I think in all of the ongoing efforts, some really strong driving points are understanding strong correlations, understanding dynamics, including thermalizations, and thinking about how cold atoms can be used for quantum simulations. And I think there are really a lot of new things, new probes, new toys that are contributing to us being able to ask these questions about how do strongly correlated systems behave. And I think sort of personally, a really nice development, I think, over the last, say, 6, 7 years or so is that there's really a drive now to have quantitative comparisons between theory and experiment. And I think that is a really nice development. So this is sort of the last slide. I'm hoping that the things that you hear today in these lectures can really form a basis for understanding what's coming in the next few days. So I've sort of tried to highlight all the types of things that derive from just thinking about alkali atoms with contact and van der Waals interactions. Thank you.